Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the histogram and kernel density estimation. First off, I would like to apologize if you hear some background noise in the video. There's this extremely annoying construction out there, down there, beside my apartment. And I mean, at some point I just need to record the video. So, I've tried to tune the gain in the microphone, so hopefully you don't hear it that much. You might have to turn the volume up a little bit. But it is what it is when you live in New York City. So let's go for it. Okay, the goal here is going to be to see how we can estimate probability density from data. In the previous video, we talked about the probability density function. It's super useful to characterize the behavior of random variables, continuous random variables. It basically tells us the probabilities that they're anywhere. It gives us a very quick visual description of where there's more probability, like the density is higher, there's less probability, the density is lower. But at the end of the day, we want to estimate this stuff from data. So how do we do it? The prerequisites for this material are mostly the probability density function. You better know what it is because we're estimating it from data. Remember that the probability density function is this function such that it tells us locally what's going on, essentially in an interval of length epsilon, where epsilon goes to 0, the probability density times epsilon would give you the probability that the random variable is there. And the definition is that it's the derivative of the CDF of the cumulative distribution function. We already explained how to compute the cumulative distribution function from data, right? Because the cumulative distribution function, or CDF, I'm going to say CDF from now on, is just a probability. It's the probability that the random variable is more than a certain value. So you can go and do what we always do, which is use empirical probabilities. We look at the fraction of the data points that are below that value, and boom, that's the CDF at that point. So now, you could say, how about we just differentiate the empirical CDF? You don't need a video for that. Let's just do that and go home. Would that work? Think a little bit about it. It would not work, because if you remember, the way the empirical CDF is computed, it's again by counting how many points are to the left, if you want, smaller than any particular value A, and computing their fraction. And that fraction only changes at the data points, okay? So here's an example where we were computing the empirical CDF of GDP per capita. The CDF here and the CDF here is exactly the same because there's a data point here and then there's no other data point until here. So because of this, the CDF is just going to be piecewise constant. So good luck differentiating something that is piecewise constant. That is just not differential. So this is not going to work. Essentially, we have limited data. We're not able to approximate a continuous CDF by this trick of considering empirical probabilities, so this just would not work. Instead, we're going to take another route. Remember that in order to estimate a valid PDF, we need to be non-negative and integrate to 1. That's something that we're going to bear in mind. That's what we want to end up with. And our strategy is going to be to not use empirical probabilities of belonging to a single point, because we already saw that that doesn't make sense, because the probability that a continuous random variable is at a specific point is always 0. Instead, we're going to actually use empirical probabilities of the random variable belonging to intervals, which is very natural because that's the way we think about continuous random variables anyways. Okay, so in order to do that, we need to make some assumption about the density. And what we're going to do is we're going to take, some inspiration from this idea that when you're very close to a certain point, you can just multiply the density times epsilon. And what we're going to say is how about we take, very small intervals so that we can assume that the density is more or less constant and just estimate it as being constant using the empirical probability divided by the length of the interval. Okay, that's what we're going to do. That's called the histogram. In particular, let's go a little bit more in detail. We're going to divide the possible values that the continuous random variable can take into bins. These are just a name for intervals that people like to use. They use bins or buckets. we're going to approximate the probability that the random variable is in each of these bins using the empirical probability, so the fraction of data that falls into that bucket, and then we're going to divide by the length of the bucket to obtain a density, assuming that the density is constant in each bin. So let me draw a picture. Imagine that we have the real line. Now you might be able to hear the construction. Okay, so this is a real line. And what I'm going to do is I'm going to say, oh, I think the random variable is between here and here, let's say. So I create 3 bins. Okay, okay, these are going to be my 3 bins. Okay, I'm going to do 4 bins because otherwise they wouldn't even be approximately the same length. And usually, I mean, you don't need to, but usually we take them to be the same length. And now we're going to say, okay, so I have this observed data, and I'm going to compute the density at each point. So what do? I compute the empirical probability of this, which is 2 divided by 4. That's the empirical probability. And let's say that the width here, I don't know, the width is W. Then the density here, I'm going to approximate it as 1/2 divided by W. Here, there's just 1 point. The empirical probability is 1/4. Here, the density is going to be 1 divided by 4W. And here, the same thing because there's just 1 point. Okay, so hopefully that cartoon kind of makes it clear. This is a histogram. If you had heard of histograms, essentially what we're doing is we're counting how many points fall into each bucket or each bin, and then we're normalizing so that that's a valid density. That's what we're doing. Okay, this might look very scary. I'm just going to walk you quickly through the notation. The idea, I mean, you should stay with this idea where you're cutting up things. We're just counting the fraction of data points that fall within each bin, and then we're normalizing. That's all we do. Okay, so the notation here is that we assume that the random variable is between m and m plus l. So in my picture here, this would be m, and this would be m plus l. And my w, okay, so, and now we're going to cut this thing up into b bins of l over b, which this would be my w in my example. Okay, and then we have this notation with which again might look very scary, but this is just computing how many data points fall within each of these bins. Okay, this is what this is counting. This is why there's this sum, and we have to normalize so that the density actually integrates to 1, and we achieve that by dividing by 1/n. Okay, that's it. So, you can go through this notation carefully, but maybe there's not even a lot of point. The point is more this picture, okay? We just divide the range of the continuous random variable into b bins. We compute the fraction of data points that fall into each bin, and we normalize to compute the density, assuming that the density is constant within each bin, which, we have to make some assumption at some point. Okay, so this is what we get if we use 50 bins for the height, for this data set that contains heights in the US Army. So just so that you see, for example, here, if you look at 170, it's this bin here. I'm going to follow it up. So approximately, 145 people have height 170 centimeters. And so on and so forth, okay? So that's what each of these 50 bins mean. And now I have to divide so that this whole thing integrates to 1 and is a valid density. I'm going to divide by the width of the bins and also by the total number of people, right? I also have to normalize the count so that it becomes an empirical probability, and that empirical probability I'm going to divide by the width of the bin. And if I do that, boom, I get a probability density. This is a probability density estimate for the height in the US Army according to this data set of like 4,000 people. So, is the histogram a valid PDF? The way to see that it is the following. Okay, so let's go back to my example because that's going to be easier. So we go to my example. I used different colors, but I hope that's okay. We had like this 4 bins, which, believe it or not, are the same length. And now I had 2 data points here, 1 data point here, I think, and 1 data point here. And now the way we constructed this histogram is basically, I'm going to do the histogram maybe in another color. I'm going to do it in green. Okay, so here we have this constant PDF, and the height here is this number of points divided by the total number of points, n, and divided by the width, right? Divided by the width. So this with W, and here we have the number of points in the bin divided by n. And here the same, and here the same. So what we can do here is we can realize that we can always cut this up into individual rectangles. Okay, so here it's very clear, there's just a single point. There's an individual rectangle which has width W and has height 1, sorry, and here actually we also divided by W, I forgot to write this. Has height, this has height 1 over n and over W, okay? Because remember that when we look at this area, that area represents the empirical probability, is the number of points that fall in between this bin divided by n, so that's why the W's are going to cancel out. So essentially I have this rectangle, and this rectangle has area 1 over n. When I have 2 points, this actually I can divide into 2 rectangles. Okay, because here I always have the count there. If I had 3 points, I would have 3 rectangles. So basically, I'm just putting rectangles in the bins according to the number of points that I have. Each rectangle has area 1 over n. There's n rectangles because those are n is the number of points. If I add up all the rectangles, the total area is going to be 1. Okay, so the answer is yes. This density estimated with the histogram is going to integrate to 1. Okay, the total area. I mean, this is a better notation, maybe. I mean, this is a notation that is more consistent with the complicated notation that I put before. I just wanted to, give you hopefully a more simple explanation using this W here. Remember that the W is just L over B. So the W is equal to L over B. So that's why I'm saying here that this is B over NW, right? So this is just 1 over NW. Okay, just so that you see that this is consistent with what I was writing. But the point is that, okay, like for each data point, you can think of this as we're putting a rectangle in the corresponding bin. That rectangle has area 1 over n. If you add up all of them, they're going to have area equal to 1. Okay, so that's what I just said. So we're good. This is a histogram with 50 bins. You can see that when we use very fine bins, because the empirical probabilities are not going to be super precise if we don't use a lot of points in each bin, that is going to result in a bit of a noisy estimate. If we make bigger bins, it's going to be much more stable. You're going to see a much smoother density, but you're going to lose details, right? You're going to lose structure that you might be interested in. And if you make it super coarse, like a very small number of bins, these probabilities are probably really good, but you don't know what's going on inside each bin. So that's the trade-off that you have when you're deciding how many bins to divide the range of the random variable. This is the GDP per capita dataset that we had looked at. Notice that when we use the histogram to approximate the density, we immediately see this, which was not so obvious when we were looking at the empirical CDF, which is that most countries have very small GDPs per capita, and then there's some that have much larger ones. And then, there's this like decaying, this weird structure with respect to the height dataset where things are very symmetric around its center, around its median. If we use more bins, again, things become smoother, but we're eating up stuff, right? Like, so this structure here let me maybe take this away. This structure here, we don't see it anymore if we use very thick bins. And again, there's this trade-off, right? Like if you use very wide bins, very long bins, long, wide, thick, I don't know, whatever you want, you're going to lose granularity. You're not going to be able to see some of the structure in the data, but your empirical probabilities that you're using to estimate the density in each bin are going to be much better. Okay, so now let's go back to this picture that I had drawn, where I had said that at the end of the day, when you are building a histogram, what you're doing, so let me see, like go back to my 4 data points again. What you're doing when you're building a histogram is basically putting this boxes. Okay, so here I put 2. Maybe this one I should have also closed it like this. It looks nicer. I put 2 boxes here, no box here. I put a box here. Wow, this is a disaster. I'm not very good at drawing, as you might have noticed, but let me do my best. And another box here, okay? Let me redraw that one. So this is how we build the histogram. We put a box for each of the data points, and the boxes are at a predefined location. So this looks unsatisfying for 2 reasons. So maybe you can think about what those reasons could be. At least 2 reasons. I would say that one of the reasons is that the location of each box does not depend on the location of the data point. Okay, so here, why wouldn't you just take a box that is centered at the data point itself? Like, why wouldn't you just put the box here? This is more reasonable, right? If you're estimating the density, you're adding boxes to build this density. Why don't you put the box centered at the data point? That doesn't look very centered at the data point. Let me try to draw it again. Centered at the data point. Yeah, assume that is centered at the data point. So that's the first thing. The second thing is that it seems kind of weird to, have these rectangles. In principle, I don't need to necessarily put a box, right? I can put anything that that integrates to 1, which is then going to be multiplied by 1 over n, so that when I add all of them, they all integrate to 1. So why not put something nicer? Let's do it here. Why not put something that peaks close to the center of the data point and then decays like this? Okay, like that. So, like maybe I'll draw it up here. So what I'm saying, because I'm starting to draw too many things over each other, what I'm saying is that, okay, if you have your data points here, and you've decided to anyways put some, some boxes on top, instead of putting boxes, you could just put something smoother that also integrates to 1, and adding all of this is going to give you the density, and then you're going to get a much smoother density. This, I think, I would claim, is a bit more satisfying than just using these predefined boxes. And doing that is called kernel density estimation. That's all it is. Kernel density estimation is just saying, oh, in the histogram, I'm fixing the boxes before even looking at the data. How about I put one box, put the boxes centered on the data? And the second step is, instead of using boxes, how about I use something a bit smoother? Okay, so why wouldn't we center them? And do these things have to be rectangular? Those are the 2 motivations for kernel density estimation. They don't have to. You can actually take an arbitrary function k, center it at the data point xi, and then you are going to see that this k that integrates to 1 has a parameter h. The parameter h, what it does is it dilates, or it basically if k looks like this, if you increase, let me get this right, if you increase h, you're going to make it fatter, right? And if you decrease h, I always get this wrong, you're going to make it thinner. And if you divide by 1 over h, you preserve the fact that it integrates to 1. Okay, so as I was saying, we're going to center these things at each data point. Don't worry too much about the notation. Let's take a look at the pictures. So, like, is the estimate a valid PDF? We'll answer that in a moment. I always like to look at the pictures first and then think about the notation. So what we're saying is we have a data point here. We're going to, use, we're going to have 3 data points, by the way. This is what there's 1/3 there. We put a rectangle of width h centered at the data point. Okay, there's these 3. This is how we're building the kernel density estimator. We're adding these 3 things. In this case, we're still using rectangular boxes. We're going to move on to the smooth boxes in a moment. Okay, so then we add another for this other data point and this other for this data point. And now the main difference with the histogram again is that these boxes are not predefined. They're centered at the data points. And when we add them all up, this is our new estimate of the density. So now we can go back to the formula. This is a sum of copies of what we call a kernel. That's why it's called kernel density estimation. Kernel is a word that people use in math whenever they don't know how to call something. Null space of a linear space, kernel. Function that we use to kind of add a kernel. So it's a bit of an overloaded word. In this case, kernel is just a function. It's just this function that we use instead of, you could also call it maybe a window or something like that. People in signal processing like to call them windows. We're using these windows or these kernels to build the density, and they are centered at the data points, as I said. And their width, we kind of decided this is going to be like the parameter that, when in the histogram we decide the number of bins that determines how wide or narrow these bins are. That's determined by h. Okay, and we have to divide by h so that it integrates. Each of these guys integrate to 1. So then we can go maybe back to the notation that was a little bit complicated, and this is this sum that I had here. And here the only thing I say is that the kernel is non-negative and it integrates to 1, so that indeed it is a valid PDF, because then you just add up the areas of each of the kernels. They're all going to add up to 1 because you have this 1/n here. Okay, and each of them individually has area 1. So again, we explained this here for the rectangular kernel, but it's more natural to use a more smooth kernel. I didn't even include it in the slides, but here what I'm using is a Gaussian kernel. You should not be confused about using a Gaussian kernel to estimate probabilities using kernel density estimation and an actual Gaussian PDF, which is what we're going to talk about in the next video, which is something completely different. Okay, that's a parametric estimate. This is a non-parametric estimate because you're just locally estimating the PDF at each point using, at the end of the day, empirical probabilities. Okay, so this is how the kernel density estimator looks like when we're using the smoother Gaussian kernels. This is what it looks for the height in the US Army when we use a kernel that is very narrow. If we make the kernel wider, this density is going to become better and better estimated because we're using more data points. So it's going to look smoother, although you might be losing some meaningful structure in some areas. Here we still see, by the way, that there's this asymmetry here where there seems to be slightly more density towards shorter heights than towards larger heights. And when we have very, very wide kernels, we might oversmooth. So here we're missing that, right? Here it looks as if things are essentially symmetric, but we see that they are actually not if we use a thinner kernel. This is the kernel density estimator for GDP per capita. Here we can clearly see that when we don't have a lot of data, we're going to see these bumps, which are the individual copies of the kernels, which are copied at each value of the data point. So there's a data point there that is Monaco and another one that is Liechtenstein. We see them clearly. If we start increasing the width of the kernel, we see that the influence of each data point goes down. The estimate is less noisy, but you might lose some structure. Okay, you get maybe the overall shape, you will get it more accurately because you're using more data points, but you might lose local structure that you're not able to estimate. Okay, so what have we learned? We have learned to estimate probability densities from data using the histogram, and then using a variation of the histogram, which is kernel density estimation, where we essentially center these boxes at each of the data points, and we can also smooth them out so that the influence of each data point decays as you go away from it. Thank you very much.